Hi, I'm Caden Slovacek, and in this video, I will once again be analyzing professional skateboarder Danny Wei's jump over the Great Wall of China. However, in this video, I will be using energy methods in order to determine the amount of work done by friction while Danny is traveling along the ramp. I've chosen to use the same example for this video because I will be using the result from the last video in order to simplify a very complex calculation. Additionally, I believe applying two different concepts to the same problem does a great job of illustrating how connected these concepts really are. I will once again start by rolling the clip. So, we will be measuring the work done by friction between points A and B marked on the image. I flipped the image horizontally in order to make Danny move from left to right, which does not alter any of the kinematic information. I will also be working under the assumption that the effective air resistance is negligible in comparison to the frictional force. Additionally, we will assume that Danny starts at rest. Without the video for reference, this would be an extremely difficult problem because the frictional force is not constant along the path, so we would have to create a function to represent the frictional force and integrate it along the path, denoted S in the image. However, I came up with a clever method to estimate this calculation without any integration required. By using energy conservation to find Danny's theoretical speed without friction, and then comparing it to his actual speed, which we calculated in the last video, we can estimate the work done by friction. I was able to find Danny's mass, as well as the height dimensions for the ramp online, which is all of the information we need to apply the energy conservation equation. After the equation is applied, we find that Danny would theoretically have a launch speed of around 18 meters per second without friction. However, recall that in the last video, we found that Danny's actual speed was only 13.5 meters per second. Since we are assuming that friction is the only non-conservative force acting on Danny, the difference between his theoretical kinetic energy and actual kinetic energy must be equal to the work done by friction. By applying this concept, we are able to find that the work done by friction while Danny is traveling along the ramp is equal to nearly 6 kilojoules. I was not able to locate a full plan for the ramp, so I was not able to determine the exact length of the path. However, if we had this information, we could divide the work done by friction by the length of the path to come up with an estimate for the average magnitude of the frictional force. I thought it was really interesting to see how these two concepts could be brought together to simplify such a complex calculation, and I hope you do too. Thanks for watching. Bye.